Hello, in this video I'm going to talk through the twin paradox, which hopefully is going to give us a better handle on frames of reference and how to transform between them in special relativity, and why this is so important to be clear about what frames of reference you're actually using. So we've seen in previous videos that all observers regard clocks that are moving relative to them as an observer. They regard those clocks as running slowly compared to clocks that are at rest relative to them as an observer. So moving clocks appear to run more slowly. Now we could extend this to people as well. So we could say, well, moving people appear to age more slowly. So this is the starting point of our twin paradox. So let's flesh this out into something which is a bit more a rounded description. We got our two twins here, A and B, and they both start off on the Earth, and A is going to remain standing on the Earth all the way through this experiment, this thought experiment. So A stays here on Earth. I mean, I say a thought experiment. You could actually conduct this. It's not something that is only can only be imagined. This could happen in real life. So A stays here on Earth. B goes on a journey. B goes off to some distant planet and then turn around and come back again. So looking at the aging of these two twins, it looks at first glance that maybe they could both say that the other one is going to be aging more slowly. From the point of view of A, at rest on the Earth, B is moving off. So B moves to the planet, B moves back again. So if B is moving, it'll age more slowly from the point of view of A. Now, couldn't we do the same thing from the point of view of B? Couldn't we say, right, well, let's take the rest frame of B, in which case A is the one that's moving. So A will be aging more slowly from the point of view of B at rest, in which case A will be aging more slowly and younger when B returns. Now, when B gets back to Earth, well, you can't have both of them have aged less than each other. One of them has you've either got to have a case where one of them's older than the other, or they both age by the same amount. So what is the outcome for this? And if they've aged by different amounts, why is that happening? Why isn't it just that both of them have got equal but opposite points of view? Right, so quick spoiler of the outcome. The outcome is that B ages less. And the heart of this is that B is changing their frame of reference. So they're changing inertial frame when they reach the planet. So B is in two inertial frames throughout this process around this trip, whereas A just stays in one inertial frame. So we've got an asymmetry there. We've got something to hang an explanation on, in that A and B are not identical in what has actually happened. Right, so let's set up some events then, so we can actually compare what events are happening and measure some times between events, because this is what we do in special relativity. We're looking at the times and locations of events. So let's kick off with B then. So here's B's frame of reference. This is the rest frame of B. We've got our X, Y, Z for space, and he's got this lamp, and he flashes the lamp when he leaves Earth. So that's at time t equals 0, and this lamp is in coordinates x, y, z in space. When he gets to the planet, now the lamp is still in exactly the same position in this frame of reference of B, because it's the rest frame of the lamp as well as the rest frame of B. So we're still at x, y, and z in terms of space, and the time now is t0. This is the time between these events. This is the proper time between the events occurring because it's in the rest frame of the lamp. Now, what is A seeing in this time? If A is having to measure the time between those events, so we need to be careful here what we're talking about. So it's the events of the lamps flashing. So the flash on the Earth and the flash on the planet. Now, obviously, it's going to take a while for the flash on the planet to then propagate over to the Earth for A to actually see it. But if when A actually records this flash, appearing on Earth and they take out the travel time, what are they going to actually observe as the time between events? So we're actually talking about time between events, not the time between events plus the travel time. So time between events, t, is going to be from our time dilation. So that's our proper time divided by the square root of 1 minus v squared over c squared. So let's use our favourite v for this, 80% of the speed of light, just because it's going to make things easier. That's the one that then comes out as giving us 5 over 3. So they're going to measure that the time is going to be 5/3 of the proper time between those flashes. So we've got this change in the measured time. Now, the same thing is going to happen on the way back. B is now going to change inertial frame because he's now going to be going in the opposite direction. And he's one inertial frame going that way, where he's got a different velocity if he's then going back towards Earth. B changes inertial frame, but you're going to have the same calculation on the way back. We're going to have a flash when B leaves the planet and another flash when he arrives at Earth. A is going to measure exactly the same time. B is going to measure the same proper time. So if we were just going to, get these up to some nice whole numbers, if B has travelled for 6 years, according to his measurement, so 3 years out, 3 years back, that's our T0, then A would have measured 10 years. So we've got that difference there in 4 years, that A has aged for 4 years more. Now, we can't do the same thing for A. We can't say, well, okay, fine, A can set off a flash when B leaves and when B arrives, but A doesn't know when B has arrived at the planet. We can't set off this flash in between. We've got this difference here of this switch when B is changing into inertial frames of reference. A can't set off a flash at that point. Now, what we can do, if you're still not entirely convinced by this, let's flesh out these calculations a little bit more then, just to really, show how much of a difference there is between these two points of view, between A and B. So say B sends a pulse every year. And I'll stick with this 3 years out, 3 years back for B. So from B's point of view, we got one pulse every year. So one pulse every year. This is years as B measures it. So it'll be sending 3 pulses on the way out and then 3 pulses on the way back. So 3 pulses out and 3 pulses back. Now, what is A going to see on this then? So as far as A is concerned, these intervals, these 1 year intervals, are going to be 5/3 of a year from A's point of view. That's what they're seeing from our time dilation. And they are going to then see, well, B has moved a certain amount. B's moving at 0.8 times the speed of light. So that is going to be, by the time we multiply these together, so we're getting 4 over 5 for our fraction of the speed of light times 5 over 3. So B would have moved 4 over 3 light years in terms of distance between those pulses. So this is what A is seeing. And they're going to receive these pulses because we've got this travel time. This is why this thing is going to be useful. These pulses are moving at the speed of light. So A will receive a pulse every 5 over 3 years for the duration between the pulses, and then 4 over 3 years for the travel time, which is then every 3 years. So they're receiving pulses every 3 years on the way out. Now, on the way back, again, you've got the 5 over 3 for the elapsed time between pulses as far as A is concerned. But now B's getting closer every time it sets off a pulse. So the travel time is going to be dropping by 4 over 3 because B's getting nearer and nearer to Earth. So it's going to then receive pulses at every 1/3 of a year on the way back. So this is on the way out. This is on the way back. So B has let off 6 pulses. So that's 6 in total. A is going to get pulses every 3 years on the way out. So that's 3 lots of 3 years, because B's sent out 3 pulses on the way out. So 3 times 3 is 9, and 3 pulses on the way back. 3 times a third is 1. So you're getting 9 years on the way out, 1 year on the way back in terms of these pulses appearing, which means we get our 10 years. We're going to get a different setup if we approach this from the point of view of B. So say A was letting out pulses. So A is letting out pulses every year. Pulses every year, just like B was doing in this. Let's change colour actually so I don't get mixed up. So A is now sending these things out. We've got the same thing that B is seeing these durations as being 5 over 3 years. We've got exactly the same time dilation going on there. So while moving away, same calculation, B is going to receive a pulse every 3 years. So exactly the same calculation as we've seen. So that means B is going to get 1 pulse on the way to the planet. So 1 pulse as it approaches the planet on way out. And then what's happening on the way back? He's going to get a pulse, receive a pulse every third of a year on the way back. So that means on the way back, there is going to be 9 pulses on the way back, because you've got 3 years and getting a pulse every third of a year. So that is going to be 3 pulses a year for 3 years. So 9 pulses on the way back. So that is how it's getting the 10 pulses turn up. But that is then 1 times 3 plus 9 times a third, which is 3 plus 3, which is 6 years. So again, you can see there isn't a symmetry here between A and B, because B is changing frame of reference when it reaches the planet. You can see it's just a completely different setup, whether you're A and whether you're B. And that is why A will be 4 years older than B when B has returned. So it really shows the importance here in knowing which frame of reference you're actually in, and then what time you're measuring between events. You know, what frame of reference are you in for measuring a time, for measuring a distance? How do you then convert that into another frame of reference? And then what does that mean in a different frame of reference in terms of measured distance and elapsed time? Now, of course, one thing that hasn't been included in this is the accelerations and decelerations that B are going to have to perform in order to accelerate away from Earth, decelerate into the planet, and then accelerate out of the planet again, and then decelerate as they come back into Earth. So there's a lot of accelerating and decelerating that B is going to have to do in order to make this journey. And we can't include that in special relativity because we're only dealing with inertial frames of reference. So those accelerations will be described in general relativity. But actually, I mean, we haven't got into general relativity, and we're not going to be getting into the mathematical details of general relativity. But when you do get onto that, if you study it at university, then you'll see that this will actually increase the age difference from 4 years to be even more when you get into the general relativity effects. So even that isn't going to make this difference go away. You know, this is an actual difference that can be measured. You know, it's not just some freak paradox or some misunderstanding. This is an actual real world difference. If you conducted exactly this experiment, you would get that result. So yeah, interesting stuff. So hopefully that's cleared up a little bit of what the twin paradox is about, and really underlying the importance of understanding these frames of reference in special relativity.